welcome to this lecture session of the course Engineering Thermodynamics. So in our previous lecture, we have seen equation of state and we have seen particularly the concept of compressibility factor. Now let us try to go into more details of the concept of energy and let us move towards our discussion on first law of thermodynamics. Okay, so before that, let me first start with the concept of energy only. Okay, so as I have already told you that energy, particularly in one form, we have seen that E is nothing but equal to U plus kinetic energy plus potential energy, where we have called that kinetic energy and potential energy are nothing but the macroscopic forms of energy, and at the same point of time we have also told that these are the energies which depends upon the physical state of the system. Okay, and U we have called as nothing but microscopic energy, and what are its different components that we are that also we have tried to see from the molecular perspective. And then this microscopic energy we are calling as something which depends upon thermodynamic state of the system. So this energy is nothing but depending upon thermodynamic state of the system. Okay, so now apart from this also what we are having, apart from these two energies also we are having more energy interaction. Okay, so how that more energy interaction takes place, that let us try to see. Okay, now what we are having, as already we have told, that if we are having say closed system, so if this is my nothing but a closed system. Okay, so what will be happening inside this closed system? Obviously, whatever the amount I am having, that will be fixed. So mass inside this system will be fixed. So if I have this system in thermodynamic equilibrium and it is having some thermodynamic state, obviously I can specify its energy content. For example, if I can mention that say it is having E1 equal to 30 kilojoule. Say the energy of this system at some point of time is nothing but equal to 30 kilojoule. Okay, now after this what may happen, this system may have some interaction of energy with its surroundings. So this is my system, so anything outside this system is nothing but the surroundings to the system, and it may have some exchange of energy with its surroundings. Okay, so now the exchange of energy which will be happening across the boundaries of the surface, that particular exchange of energy is something which can happen particularly in two ways. Okay, so the exchange of energy which happens across the boundary of the system, that particular exchange of energy is categorized into heat and work. Okay, so it means heat and work, these are nothing but forms of energy only. So these are also some another form of energy only, and due to these energies, so these are the energies which are associated with exchange of energy content between the system and surrounding, that will be particularly happening through the boundary of the system. Okay, so one of the important point is that these two energies are something which takes place at the boundary only. Okay, so what is the meaning of this? Let me just try to explain with the help of one example. So let us consider that we have some hot block. So we have some hot block. So the meaning of hot block, why I am calling it as hot, say this block is having temperature T and surroundings is having temperature TSUR. Okay, so we are calling this block as hot because its temperature is more in comparison to temperature of the surroundings. Okay, now let me consider that initially this particular block is having say energy content of 2 kilojoules. Okay, So now what I am saying that this block is having some energy content of 2 kilojoule, and as its temperature is more in comparison to temperature of surrounding, so what will be happening? We all know that we will be having some flow of heat to the surroundings. Okay, so now let me consider this arrow say particularly represent the transfer of energy that is being taking place across the boundary. So when we are having any energy which is crossing through the boundary, so we will be having some energy say 2 kilojoule now which is crossing through the boundary. Okay, and finally we will be having situation when this 2 kilojoule of energy has reached into our surrounding. So now we will be having 2 kilojoules of energy over here in surroundings. Okay, so now there are three different situations. So first is we are having this 2 kilojoule of energy within the system. So when we are having 2 kilojoule of energy within the system, we will be saying that this energy is nothing but stored within the system in the form of its internal energy. Okay, so when we are saying that 2 kilojoule of energy is there within the system, that energy is nothing but stored in the form of its internal energy. Okay, and when we will be talking about the surroundings energy, once again when we are talking about surroundings, actually energy has come out of the system, and this 2 kilojoule content of energy has been absorbed by the surrounding. So that's why surrounding will also be absorbing this 2 kilojoule of energy in the form of its internal energy. Okay, and in another way, we sometimes also call this type of energy as thermal energy also, but more often we use the appropriate term is nothing but our internal energy. Okay. Now we are having the same energy content while it was passing through this particular boundary. Now what will be happening? While the same energy content is passing through this particular boundary, we have to call this energy either as heat or work. Okay, so this is one very important point, that when we are having any energy content within the system, if it is within the system, it will be referred to as internal energy. Once again, if it is there in the surrounding, so surrounding is nothing but some another system, but we are not actually considering it into consideration, so that's why we are calling it surroundings. Okay, but here also, like once the energy has come out of the boundary, now it is nothing but absorbed by this boundary, so that's why here also it will be stored in the form of internal energy. So it means internal energy is something which is kind of related to the storage energy, or in other words, I can say that whatever the mass system is having, that mass is actually possessing certain amount of energy, that we are calling as internal energy. Okay. Now, while we are having any form of energy which is actually crossing through the boundary, okay, or I should say that if it is crossing through the boundary, it means this energy is nothing but in transport. So this energy is in the state of transport or transfer. So when we are having any energy content which is actually in the state of transfer or transport, so that particular energy content, or I should say the energy which is associated across the boundary of the system, that particular energy we are calling as nothing but our heat and work. Okay, so it means that earlier we have seen kinetic energy, potential energy, internal energy, but now we have come up with a few more forms of energy over here, and we are calling these two forms of energies as nothing but our heat and work. Okay, and the characteristic of these forms of energy is that these only comes into picture while energy transfer is taking place. Okay, so now it becomes the important point that energy in transfer already we have got nothing but our heat and work, but what is the difference between the two? Okay, so now the important point is what is the difference between heat and work. So now how we differentiate any content of energy which transfers because of temperature gradient. So any transfer of energy across the boundary which will be happening because of the temperature gradient, or I can call it as also temperature difference, that particular energy content is something which is referred to as heat. Okay, and any content of the energy that will be transferred not due to temperature difference, so that we call as nothing but our work. Okay, so this is the important distinction between the heat and work. Okay, so the first important characteristic is that heat and work both are the forms of energy which comes into picture while we are having transfer of the energy across the boundary. So while we are having energy in transfer form, at that time only these come into picture. But how to differentiate in between heat and work, that while we are having some energy transfer across the boundary, whether it is a heat energy or it is a work, so how to differentiate? So that is something we are having actually. The driving potential of that particular form of energy is responsible for categorizing. For example, if we are having temperature difference between system and surroundings, and because of the temperature difference, whatever the energy transfer will be taking place, we will be immediately categorizing that into heat energy. And if we have any transfer of energy which is not because of the temperature difference, that particular thing we will be calling as nothing but our work. Okay, so it means apart from the storage internal energy, kinetic potential energy, we are having two important forms of energies, heat and work, which only comes into picture while we are having transfer of energy. Okay, this particular thing is applicable up to the closed system. So while we will be going for the open system, obviously these will be applicable, but apart from that, we will be having actually the transfer of mass across the boundary. So that transfer of mass also will be carrying certain amount of energy. So that we will try to see in our subsequent lectures while we will be doing the analysis of open systems. Okay, so at the moment, with reference to the closed system, you have to only remember that apart from energy in storage, we have energy in transfer also, while some thermodynamic process will be happening, and that energy in transfer will be actually responsible for heat and work in that system. Okay, so let me once again illustrate with the help of an example. So let me consider that I have some system which is having, say, 30 kilojoule of energy. Okay, and outside I have nothing but my surroundings. Okay, now once again I will be saying that my T system is greater than T surrounding if my outside temperature is surrounding temperature. Okay, now say that because this temperature was greater than surrounding temperature, so some amount of so initially, now at the first point, you see, so at the first point what we were having, basically we were having energy content of the system as nothing but E1 equal to 30 kilojoule. And if you talk about heat and work, so heat and work at this particular state were nothing but equal to 0. Okay, so now what will be happening, say, because our system is greater than surrounding, so obviously some process will take place. Okay, so now the process has taken place in such a fashion so that 2 kilojoule of energy has transferred from system to surrounding. Okay, so why only 2 kilojoule has transferred? Let us consider that after the transfer of 2 kilojoule of energy from system to surrounding, say our system temperature has become equal to that of the surrounding temperature. Okay, so now what will be happening? Now our system will be reaching to some another thermodynamic state where I can say that my T is nothing but equal to T surrounding. Okay, so how this has happened? This has happened once system has transferred 2 kilojoule of energy. So now, while this 2 kilojoule of energy was being transferred, this particular 2 kilojoule of energy I have to call as nothing but my heat energy. Okay, so once the system temperature has become equal to surrounding temperature and 2 kilojoule energy has gone from the system to the surrounding, so now within my system I will be having only 28 kilojoule of energy. Now you can clearly see that temperature of the system has also changed and energy content of the system has also changed. So now it will be reaching to some another thermodynamic state E2, where our energy is actually 28 kilojoule and heat and work is once again equal to 0. Okay. So it means that while a system is in thermodynamic equilibrium state, at that particular point, value of heat and work is equal to 0. So it means heat and work are the forms of energy which are only applicable while certain process is happening. Okay. While a system is in thermodynamic equilibrium, at that point, the value of heat and work is equal to 0. Here you can clearly see while we are having the transfer of energy, during the transfer of energy, obviously our this one you can see that we were having 2 kilojoule of the heat which was associated across the transfer. But between the two thermodynamic states, obviously, while we have reached to the equilibrium thermodynamic state, at that point, our value of heat and work is equal to 0. So clearly, if I try to plot this one, say on my temperature and energy, say temperature and energy diagram. So initially, we were having system temperature some say T1 and say this is my T2. So at T1 temperature, I was having energy content as E1, and at temperature T2, I have now, so at T1 temperature, I was having energy content E1, and at some temperature T2, I am having now energy content E2. So I can call this my as first state, and this I can call as my second state. So you can clearly see that while we are at first state or we are at the second state, at that time heat and work is equal to 0. Only while we were transferring from first to second state, during that time only we were having actually heat. So similarly, during that time only we will be having work also. Okay. So it means heat and work are the forms of energies which are associated with the process or path of the system. Okay. At any given thermodynamic state, these cannot be defined. So overall energy content, because it can be, so if I write E, then if I write heat, and if I write work, so I can say that my energy is nothing but a state function, because it can be defined at any given thermodynamic state. However, heat is nothing but my path function, because it cannot be defined at any thermodynamic state. However, it is associated with the process, with the boundary work, so that's why it's a path function. In the same way, work is also a path function. So because of that, what will be happening? Energy is my exact differential, whereas the heat and work are actually inexact differential. Okay, so this is also inexact, this is also inexact differential. The meaning of exact differential and inexact is that if I write dE, so I can simply write dE equal to E2 minus E1. So it means dE represents over here nothing but change of energy. So the change of energy I can simply write as difference between the two thermodynamic states. Over here, if I write, I cannot write over here as d heat. For example, normally for heat we use symbol Q. So I cannot write over here dQ. Okay. Why I cannot write dQ? Because it is not equal to Q2 minus Q1. Why it is not Q2 minus Q1? Because we have seen that Q2 is 0, Q1 is 0. It means when we are at any thermodynamic state, at that time heat and work are not defined, because heat and work are only associated when we are having transfer of energy. Okay, so because of that, this is an inexact differential, and I have to write del Q. Okay, so del Q I'll be writing, and I cannot write this del Q as Q2 minus Q1. Similarly, for work also, I have to write over here nothing but del W. So these are nothing but my inexact differentials. Okay, so which are associated with the process, with the transfer. These cannot be presented in the storage form. Okay, so now one important point also I would like to now highlight. So we have seen that we have certain amount of energy. Okay, so the example, for example, I have taken earlier. So what I told over there in that particular example, I have shown that initially system was in some E1 thermodynamic state. Okay, and it was having say E1 as energy content, and because of that we have now some say Q amount of heat transfer place, and because of this q amount of heat transfer, what has happened now, E2 has become the new system state, and that E2 was nothing but equal to E1 minus q. At the same point of time, if I talk in terms of surrounding, so whatever the loss within the system has taken place, that same gain has happened actually in our surroundings. Okay, so system energy has decreased by amount q. So where that system energy has gone, ultimately that energy has gone into our surroundings. So because of that, q amount of energy has increased in our surroundings. So it means that energy is something which is a conserved quantity. Okay, so energy is nothing but a conserved quantity, and what we are doing, this is something which we cannot be created and can't be destroyed. So energy is something which cannot be created and destroyed. Okay, so energy is nothing but our conservative quantity. For example, if you talk about fuels, what happens in case of our fuel? Say we are having methane. So in case of methane, we will be having energy stored in the form of its chemical energy. Okay, and while we will be burning that fuel, that chemical energy will be actually converting into nothing but our heat energy. Okay, and if we are further using that heat energy into our some mechanical arrangement, like we use in our IC engines, so that heat energy then will be converted into work energy. So it means that energy is something which is a conserved quantity, so we cannot create it, we cannot destroy it. The only thing we are doing is actually we are converting that form of energy, converting the energy from one form to another form. So it means whatever the loss of energy will be happening from the system, same amount of gain of energy will be happening in our surroundings. So if we take the combination of system and surrounding, that we call as our universe. So the energy content of the universe will always remain constant. Okay, now I have given you the details about the heat, where I have specified you that any content of energy which is transferring because of the temperature difference, that particularly we call as nothing but my heat energy. Now heat can be transferred in various ways. So the three fundamental ways of transfer of heat are nothing but our conduction heat transfer, then we have convection heat transfer, and the third way we have nothing but our radiative heat transfer or radiation heat transfer. Okay, so now in case of conduction heat transfer, already we know that we are having Fourier's law of heat conduction, which tells that Q is nothing but equal to minus Ka dt by dx. In terms of convection heat transfer, we have Newton's law of cooling, which says that Q is nothing but equal to HAS into Ts minus T infinity. And in terms of radiative heat transfer, we have Stephen's Boltzmann law, which tells that Q is nothing but equal to epsilon sigma into Ts power 4. Okay, so these are the fundamental laws which governs the heat transfer, or I should say the rate of heat transfer. So obviously, while I am writing these laws, I have to write over here Q dot, because Q I am using as the amount of energy. So the rate of transfer of energy is something which will be represented by Q dot. So I will not go into details of these three things. So this is just for your brief knowledge. I have told you that heat can be transferred by any of the three modes: conduction, convection, and radiation. And these are the equations for estimating the rate of heat transfer. However, this is not the part of thermodynamics. Okay, so rate of heat transfer is more required when we will be studying the subject of heat transfer. So that's why I will not go into much details. Okay, now let me just go into the details of work. So work, we have already defined that any form of energy which is actually not transferring, so which is transferring not due to temperature gradient. So any transfer of energy which is not happening because of the temperature gradient, that we call as nothing but our work. Okay, so now let me specify the different forms of work. So we are having the very first important form of work which we call as nothing but our displacement work. Okay, so the meaning of displacement work is that say we are having some piston cylinder system. So because of the gas pressure, high pressure gas, piston will be expanding and it will be doing certain amount of work. We may have another important type of work which is particularly referred to as shaft work. So what we say, the meaning of shaft work is that we are having some shaft on which is rotating under the action of certain amount of force, and upon the rotation of the shaft we are getting certain amount of work. Okay, we may have another form of work, so that is particularly referred to as electrical work. So how electrical work will be coming into picture, that also I'll explain to you. Okay, so it means that apart from these fundamental forms we may have, so these are nothing but all the fundamental forms of the work. Apart from these also we may have association of the work in many other ways. But mainly if we talk about our thermodynamic system, these three fundamental forms will be applicable everywhere. Okay, so let me first give you the demonstration for displacement work. So if I talk about displacement work, so let me take the example of an piston cylinder system. Say this is my cylinder, okay, and I have a piston over here, and say initially this piston is some at some location having pressure P. Inside this gas pressure is P, okay, and now because of this gas pressure, say now this my piston is actually expanding. Okay, so if say piston is actually traveling through some distance dx, and say F is the amount of force which is acting on this particular piston, so we will be having our delta W, small amount of work, as nothing but equal to F into dx. Okay, now if A is area of cross section of the piston, so obviously whatever the force will be acting on the piston, that force will be nothing but because of the that will be because of the pressure only. So we will be having pressure as nothing but equal to force. Force is nothing but equal to pressure into area into dx. Now A into dx, I can simply write area into dx as nothing but my volume. So my dw will be becoming P times dg. Okay, so now if I have to find the total amount of work in some thermodynamic process, so I have to do integration of del W, say from 1 to 2, so that will be my nothing but integration 1 to 2 P dV. Okay, so now say if I plot the PV diagram for this particular process which is happening over here in this piston cylinder arrangement. So what will be happening? Initially I'll be having some high pressure and some say initial volume as V1 and say pressure as P1. So obviously while we will be having expansion of the piston, if expansion is happening in quasi-static manner, I can actually specify the path of the process. Say this is my path of the process, and with the expansion the pressure will be decreasing and volume will be increasing. Say this is my V2 and P2 as the final thermodynamic states. So what will be happening now if I define, say this process path is nothing but A. So now what I can write, this integration of del W I can write over here as W1 to 2. Okay, so this W1 to 2 represent that this work while our process, our system is changing from thermodynamic state 1 to thermodynamic state 2. Okay, apart from that, I can also use one more subscript with this 2. I can write over here A. So over here A will be representing nothing but the path. Okay, so if my process is happening through path A and my displacement work is nothing but equal to integral of PdV. So this integral of PdV will be nothing but my this area over here. Okay, so whatever the area I am showing over here, this hatched area will be nothing but my PdV integration. Okay, now if say my process has taken place in some another path B. So if the process is happening through some another path B, in that case what will be happening? Now my amount of work will be nothing but W 1 to 2, where B will be my path of the system. And obviously this now amount of work, whatever we are getting now, that will be different, because once again it is nothing but equal to integral PDV from 1 to 2, but now this integral is actually happening along path B. So if we go with path B, we will be having some additional amount of work. So this additional amount of work actually we will be getting, because integral PDV, we will be getting this additional work over here. So it means that work is a function, work is actually a path function. In the same way, heat is also a path function, because these are particularly depending upon the process and the way process is actually happening. And we cannot define these on the thermodynamic state. Okay. So like heat, work is also a path function. So this particular type of work which is obtained by this relation PDV, this particular work is actually called as nothing but our displacement work. Okay. So this particular type of work we call as nothing but our displacement work. Okay. Then next we are having shaft work. So shaft work is actually very common in case of our turbines, etc. While high pressure steam expands on the turbine blades, because of that turbine rotates. Okay. So let me just briefly explain you about the fundamental formulation of shaft work. So while we are defining the shaft work, we will be considering, say we are having some rotor, and this rotor is actually connected to some shaft. So here we are having some shaft over here. Okay. Now let us consider that T amount of torque is acting on this particular rotor. Okay, and N is the number of revolutions this rotor has rotated upon the action of this T amount of torque. So obviously, if I define R as my radius of the rotor, so in that case, what will be happening? I'll be having certain F amount of force which will be acting on this rotor, and I can simply say that my torque will be nothing but equal to F times R, and R will be equal to, and F will be equal to nothing but T divided by R. Okay. So now if I say that this F amount of force is actually acting on the periphery of the rotor, and this periphery of the rotor is actually undergoing through certain rotation. So it means the periphery of the rotor will be having some displacement. Okay, so periphery of the rotor is actually undergoing through the displacement. If I represent that displacement with S, I can write that S will be nothing but equal to 2 pi r. So 2 pi r is my one circumference, and now how many number of rotations we are having, that is nothing but N. So 2 pi r into N will be my displacement of this particular rotor. So over here I will be able to define amount of work as nothing but equal to force into S. Okay, so force is T by R and S is 2 pi R into N. R will be cancelling, and I'll be finding W as nothing but my 2 pi N T. And if we talk about that we are having these rotations continuously happening, it means if rotations are per unit time, so if I define some N dot, which is nothing but N by T, so if I use N dot, then obviously my W dot will be coming, which will be nothing but W by T, which is 2 pi N by T into T. So N by T I am defining number of rotations per minute or per second. So in that case, I will be finding 2 pi N dot T as my work in nothing but the rate form. Okay, so this particular type of work is something which is called as shaft work, and majority of the work whatever we will be finding in our thermodynamic system, these can be obtained using these two fundamental forms, displacement work and shaft work. Okay, now apart from this, we have defined one more form of work which I have called as nothing but my electric or electrical work. Okay, so what is this electrical work? That is something which is actually quite surprising. So let me explain this with the help of one example. So let me define an isolated system. What I am saying, that I have one isolated system. So the meaning of isolated system is or rather than isolated, it is better to call this system as nothing but adiabatic system. Okay, so what I have nothing but an adiabatic system. So the term adiabatic is referred to a system where we are not having any heat transfer across the boundary of the system. So we are calling adiabatic system. It means we are not having no heat transfer across boundary. So when we are having a system for which we are not having any heat transfer across the boundary of the system, that particular system we call as nothing but our adiabatic system. So what I am doing, I am saying that we are having an adiabatic system, and inside this adiabatic system we have say some heating coil attached. Okay, so over here inside we have some heating coil, and this heating coil from outside is actually subjected to say voltage V. So this is subjected to voltage V. Now what we are doing, we are saying that whatever the system we are having, boundary of this system is fixed. So we have nothing but fixed boundary system, and we don't have any rotor. Okay, and at the same point of time, no rotor is there. So if we are not having any rotor, so obviously we will not be having the shaft work. If the boundary of system is fixed, we will not be having any displacement work. And if our now system is actually adiabatic, so we are not having any heat transfer. Okay, but we are having a heating coil, and this heating coil is actually part of the system only. Okay, so because of that, and from the outside we are subjecting some V voltage, and because of that our some charge is actually flowing into the heating coil. Okay, so we will be having, because of the charge, say Q is the amount of charge, so I will be nothing but Q divided by T, where I is nothing but our amount of current which is flowing through the heating coil. So now what will be happening, initially if you see, while the heater was not switched on at that time, say the temperature of the system was T1 and energy content was E1. Okay, once you have switched on the heater, say for some duration T, and after time T, if you see, you will be finding that your system is having some another temperature T2 which is greater than T1, and another energy content E2 which is greater than E1. So it means in this particular system now, if you try to see, we are not having any heat transfer. So heat transfer is zero. Why heat transfer is zero? Because we are saying that our system boundary is adiabatic, or the another way of making heat transfer is zero. You just take the system temperature equal to surrounding temperature. So let's say my T surrounding is outside temperature. Okay, so one of the ways to make our boundary perfectly adiabatic, or another thing we can do, we can make our system and surrounding temperature as equal. So if these are equal, our heat transfer is nothing but equal to zero. And if we talk about PdV work, that is also zero because boundary is fixed. And if I talk about shaft work, that is also equal to zero because we don't have any rotor. So it means that initially the energy content was E1, and finally we have got some energy content E2 which is greater than E1. So it means that certain amount of energy has been added into the system. Okay, so now any energy which is added through the boundary, so that energy has to be only two forms. Either it has to be heat or it has to be work. Now, because heat is not applicable for this particular system, so it means that whatever the energy is entering, that is nothing but in the form of work only. Okay, so what type of energy is entering? Nothing but we are having voltage over here, and we are having some current, so that flow of current or flow of charge is actually causing certain amount of work. So that type of work we call as nothing but our electrical work. Okay, so in this particular system, electrical work is actually happening. Okay, so now if you try to find out the amount of work, so amount of work W will be nothing but equal to W electric will be nothing but equal to voltage into charge. Okay, so that is will be our work. And if I have to find out the rate of work transfer. So if I write WE dot, that will be nothing but WE by T. So that will be V into Q by T, and Q by T we know as current. So it means it will be nothing but equal to V into I. So rate at which electrical work will be done over the system, that will be nothing but equal to V times I. Okay. So these are the different fundamental forms of work, and why we call the heating or the increase of energy content of the system because of electricity as electrical work. That also I have just shown you over here. Okay. Now let me just define the another very important law. That particular law is called as law of conservation of energy. Okay, so another important law is law of conservation of energy. So if I talk about closed system, I am now not talking about open system, because in case of open system, there will be some inflow and outflow of the mass that can also cause the change of energy. But at the present moment, we are only talking about the closed system. So for closed system, we will be only having the interactions in the form of heat and work. Okay, and we will be having inside energy content of the system as nothing but E. Okay, so if we are having this type of system, so law of conservation of energy will state that whatever Q input I am adding, okay, minus whatever the Q output is going from the system, plus whatever work input I am adding to the system, minus whatever work which is going out of the system, that will be nothing but equal to E2 minus E1. Okay, or I can call it as delta E is nothing but change in energy content of the system. Okay, so because the energy in a closed system which will be transferring, that will be in the form of either heat and work. Okay, so because of that, if I have to write down over here, so I can write that net amount of heat transfer and net amount of work transfer is nothing but our change in energy content of the system, and this particular law is nothing but our law of conservation of energy. Okay, so now in general form, if I write, many times we write as Q minus W equal to delta E. Okay, where Q we call as net amount of heat transfer. So net amount of heat transfer, which we call as nothing but my Q in minus Q out, and W we call as nothing but net amount of work transfer. So one important point you can note now, while I am talking about heat and work, I am writing word transfer also over here. Okay, so because heat and work are something which are associated with the transfer across the boundary. So this net amount of work transfer we write as nothing but W out minus W in. So where W out is actually work done by the system. So this is work done by the system, and W in is nothing but work done on the system. So if the force is acting from outside and it is actually doing work on the system, that we call as W in. If force, because of the system force, now boundary is expanding and system is doing the work against the surrounding, that we call as work done by the system. So if we talk about sign conventions, normally we take this Q in as positive, heat added to the system is positive, and heat going out of the system as negative. And work done by the system we take positive, and work done on the system we take negative. So now, if with these conventions, if you substitute in this particular equation by following these conventions, you will be finding that Q in minus Q out will be equal to, now the definition of this work is nothing but W out minus W in. W out I will be writing positive, so outside we have negative sign, so because of that automatically it will be coming negative, and this work done which is on the system, it is having negative sign, so because of that automatically it will become minus, minus will become plus. Okay, So you have to actually now stick to this particular definition of work. So while you are using this generalized form of the equation, which says Q minus W equal to delta E, you have to stick to this particular definition, that W over here is nothing but refers to the net amount of work transfer, which is nothing but W out minus W in. Okay, where W out is work done by the system, which is taken as positive, and work done on the system is taken as actually negative. Okay, so this particular relationship we are obtaining over here, and we are calling this as nothing but our law of conservation of energy. Okay, now what I will do, I will stop at this point, and we will have our further discussion in our next lecture.